Okay, we're recording. All right, so yesterday we left off with example 2, where we looked at a cubic function, and because it was a cubic function, we know that its basic shape is like this. It goes down forever to the left, up forever to the right, and we know it's continuous. So that means that we know there's no absolute maximum or minimum. So if it has maximums or minimums, or maxima or minima, I should say, then we know that they're just local. So to find them, we went through the equation, we went through the derivative, we did an interval test to make sure that the points where the slope is 0 have an increasing on the left and a decreasing on the right, which tells us that this point here, since it's increasing to the left of our point and decreasing to the right, that tells us that it's it's a local maximum. And then for the next point at -1, it was decreasing to the left of it, but increasing to the right of it, which tells me the same thing the graph tells us, that it must be a valley. It must be a local minimum. Okay, now this function again doesn't have an absolute maximum or minimum because the arms go forever in both directions. What if they don't? How do you tell if a function that is bounded has an absolute maximum or an absolute minimum? If I restrict the domain of this thing, how can I tell without graphing it if, for example, this point is lower than whatever point over here that I might end my graph? So that's where we're going to go today. So example 3 is actually the same question as example 2, but now I've actually put boundaries on the function. We're going to find the absolute maximum and minimum values of the function. So we're going to pretend like we didn't just see that graph. We're just doing this without a visual. And we're going to just, again, assume that all of the work we did in example 2 has already happened. We've found those critical values, and we're going to now find out if those local maximums and local minimums are in fact absolute maximums and absolute minimums. So putting this into kind of a more notesy form here, I'll say that we already know that x equals -3 is a local max. Maybe I'll put a comma, but is it an absolute max? And similarly, we know x equals -1 is a local minimum, but, is it an absolute minimum? So that's where we're going to get started today on example 3. And so what's our strategy here? What would prevent our x is -3 spot from being an absolute max? Well, what would prevent this from being an absolute maximum is if the function at this end point to the right, when x is 1, has a higher y value than the y value here. So what we're going to be doing is we are going to compare f of x values of the endpoints to the f of x values of the critical values. So let's start with the endpoint. So the endpoint, let's find f of the negative 3.5, right? Because go back to the function here. We're bounding this function. It goes as far left as negative 3.5 and as far right as positive 1. So let's find out what the y value is as far left as this function can go. So that's going to be negative 3.5 cubed plus 6 times negative 3.5 squared plus 9 times negative 3.5 plus 2. And I already ran this through the calculator, so I know that this is 1.125. So that means that the end point is actually the coordinates negative 3.5, 1.125. And what is that telling us? Well, this is, remember, this is how this function looks. We know it looks something like this, right? This point, oh, sorry. This point here is actually, well, actually, I just drew that bad. This, let me start this over. This point here is still positive in the y values, so it's actually still something like this, right? We know that, and I keep putting an arrow at the end when I mean to put a dot. There we go. We know that this dot here is still positive. Meanwhile, back at our local minimum, which was negative 1, f of negative 1, that's a negative 1, sorry, is negative 1 cubed plus 6 times negative 1 squared plus 9 times negative 1 plus 2. When you run that through, you get negative 1 plus 6 is 5, 5 minus 9 is negative 4, negative 4 plus 2 is negative 2. So my critical value has a y-coordinate of negative 2. So I know right away that this point here is lower than that point. Therefore, negative 1, negative 2 is an absolute minimum. Okay. And we can similarly figure out if this point, which was when x was negative 3, remember that, is higher than this point here where the graph ends. So let's do the endpoint first. The endpoint happens at, where's the endpoint? The endpoint happens at 1. So how high is the graph when x is 1? What's f of 1? So f of 1 is going to be 1 cubed plus 6 times 1 squared plus 9 times 1 plus 2. Put all that through the calculator and you're way up there at 18. So this is the point 1 comma 18. Meanwhile, our critical point happened at negative 3. So is this negative 3 point here higher than 18? Well, let's take a look. We have negative 3 cubed plus 6 times negative 3 squared plus 9 times negative 3 plus 2. And that's going to actually equal, let's see, that's negative 27. That's positive 27, or sorry, that's negative 27, that's negative 27, and that's positive 54. So all that cancels, so the answer is actually 2. So the local maximum was a maximum of 2 units high. Meanwhile, the endpoint's 18 units high. Therefore, the critical value, negative 3, 2, is only a local max, and the endpoint is an absolute max. And you might be again thinking, well, how do you know there isn't some other maximum between these 2 points? Well, there can't be, because again, I know that a cubic can only change directions twice. So now I have a really good, without having seen my Desmos picture, again, I'm pretending I haven't already looked at this on Desmos, I actually have a pretty good picture of what this thing looks like, right? I have 118 is where the end point is, so that's, I don't know, about there maybe. My other end point was negative, what was it again? Negative 3.5 and 1.125. Now I'm on a scale of 5s here, so that's negative 3.5 and 1.125 wouldn't be very high, it'd be maybe there. And I know it changes directions twice. I know it has a local maximum at what was my local maximum again? My local maximum is negative 3, 2. So negative 3 and 2. Oh, 2 is about a little under halfway there, so something like that. And then I know it has a local minimum, or in this case it was an absolute minimum because it goes lower than this point. And that absolute minimum was negative 1, negative 2. So there's negative 1, and negative 2 would be maybe about there. So now I have a pretty good kind of feel for what this function looks like. It has to go down that way, and it has to go up this way. Oh, and I actually could figure out the y-intercept really easily. Notice the y-intercept happens when x is 0. So if all of these numbers are 0, we know we go through x is, or y is 2, so maybe about there. And there we go. And there we go. There's our function, sketched without really doing a whole lot of work. We certainly didn't have to make a table of values. And you know, it's nice if we did know what these x-intercepts are, but I don't think that equation was factorable, so you'd have to break out some sort of cubic formula to figure that out. And if you want to kill an afternoon, feel free to Google the cubic formula. It's just like the quadratic formula, only way, way more complicated. So this is a fairly easy way to get a nice sketch for the function, and in your assignment you're going to have some questions like this. Feel free to use Desmos to kind of check your answer. I'm pretty sure I've shown you this at least once before, but I'll show you again. If on Desmos you would like to do what we have here, which is put boundaries on your functions, it's actually not that hard. You go to Desmos. So here's the function before I put boundaries on it. To put boundaries on it, you just type in the function and then use this curly bracket here. And let's see, can I move over? And type in the restriction exactly the same way that it's written down on the page. And notice that it stops. Here, let me get rid of the other one. There we go. It stops. And you can kind of see now that our answer was completely and totally true, right? This point here is not as low as that one, so this one is an absolute minimum. But this can only be called a local maximum because meanwhile over here, it gets way higher at the end point. So there you go. That's basically lesson 2. I'll give you the rest of this class to work on the assignment. The assignment is here on the blog. If there's people still finishing up the 4.1 questions, you can finish up those. But if you're ready to move on to 4.2, we're going to get you to do 1 to 7. Okay. If anybody has any related rate questions, we're closing in on the test for that for Friday, or implicit differentiation questions. We could spend a few minutes going over some of those. Okay, so I have a question on the chat that says, do you mind clarifying local values one more time? Well, again, what we mean by local values is that this point here is only a maximum in this local area, right? It's only a maximum here because everything to the left of it's going down below it, and everything to the right of it's going down below it. In other words, it's increasing until I get to this point, and it's decreasing after that point. That's what makes it a maximum, but I can't call it the maximum of the entire function because over here it gets way higher. So it's not an absolute maximum, it's only a local maximum. Does that answer your question? Cool. Okay, so I'll stop the video because the lesson's over. But if anybody has any questions, we could take questions.